Welcome to this presentation, an introduction to the Zero Trust Framework. My name's Simon Clifford, and these days I'm pretty much an evangelist to the Zero Trust cause. I've spent the last 25 years in designing and operating perimeter security solutions, so I really do appreciate the frustrations that businesses face in trying to keep up with the pace of change in the security landscape. I've witnessed such struggles firsthand on countless engagements, and in my experience, businesses are simply failing to tame the beast, which is complex security technology integration. So there's never been a better time to pause that technology button. The real problem here is one of strategic defense. The reality is the game has now changed, and that the old adage of defense in depth and castle walls has crumbled. There are no longer any walls to defend. Today, the fact is that the continuing pursuit of a legacy network security strategy is pretty much futile in today's threatscape. So companies need to stop. They've missed the turning. In terms of strategy, the signpost they were looking for is one which says Zero Trust. This is the first in a series of presentations that will explore both the theory and adoption of the Zero Trust framework. You can find this guide and the complete series in the tech repository at ztsec.net. So to understand why Zero Trust is so fundamental to achieving any sort of assurance in terms of your defences, let's establish what topics we're going to cover in this introduction. Please be aware that this is a series of guides. We'll be taking Zero Trust one bite at a time. Zero Trust, you will soon discover, is one big beast. So for those of you looking for the more practical aspects, such as vendor alignment, deployment strategies, and implementation guides, then I suggest for you to get to grips with the theory first, and then launch into the adoption techniques, having firmly understood the fundamentals. So the first section outlines the fundamental flaw in network perimeters and associated defense in-depth strategies. This section effectively defines the rationale for Zero Trust. Following on nicely from the background behind adoption of Zero Trust, we will introduce the tenets of Zero Trust. These are the foundations, the golden rules from which all other definitions are referenced. It is vital to interpret these correctly. This will help you cement your understanding of the more complex topics that we're going to introduce in subsequent deep dives. Finally, we are going to describe at a high level for now the functional elements of the Zero Trust framework. Many of these elements should be familiar if you already understand network security, but the real magic of Zero Trust is how they are organized and utilized to uphold the golden rules. All will become clear, hopefully at the end of this session, and I hope I will have whet your appetite to learn more. Finally, this presentation, along with this commentary within the speaker notes, can be found on my repository at ztsec.net. Let's crack on. So in this diagram, we can see the legacy network just described, alongside the perimeter-focused defense strategy. This strategy uses firewalls to control access from what it considers less trusted networks to the corporate network. So in this case, we can see firewalls controlling internet access, DMZ, WAN, and VPN. These firewalls could be separate hardware devices, or a single firewall with multiple interfaces connecting to those other networks, or indeed logical firewalls potentially, on a consolidated platform, for example, sometimes referred to as a vSys or a context in the case of Cisco. But what about inside the corporate network environment itself? Well, the legacy strategy has been to create zones, a group of equivalent trusted networks and their attached hosts, and then use of firewall control access between these zones. This diagram shows these logical zones and how the firewalls are deployed to control access between them. In this case, the zones defined are production and development server zones, corporate users, and wireless. But of course, there are likely to be many more zones in larger corporate networks. But add these firewall policies to those protecting the external networks defined earlier, and the number of access policies protecting these zones grows significantly. In fact, that's an understatement. Take the example above. With only 8 zones defined, including WAN, remote user, and DMZ, the total number of access control policies required grows up to 56. What chances, then, do network security admins have of maintaining tight access control in the light of such complexity? The answer, as we all know, is little to no chance. And that is why internal corporate networks are, by definition, not really private. Any successful violation of the external perimeter, or indeed insider with malicious intent, will be presented with a core network that cannot be defended. That is either because access control policies are ineffective, as the demands of segmentation explode traffic flow permutations, or because the challenge of internal access control has been pretty much abandoned under the excuse of internal traffic equals trustworthy traffic. So intruders can pretty much move laterally and at will within these corporate networks, the definition of a soft core. And as public cloud migrations come to the fore, the problem becomes more acute. Now, the internal networks, server hardware, operating systems, and virtualization can all be owned and managed by service providers. The shared responsibility security model of public cloud turns those networks into, at best, semi-trusted. But actually, who defends their public cloud like their internet DMZ? Most don't even deploy full next-gen firewall technologies due to the complexity in most cases, instead relying on network access control lists and, for the likes of AWS, security groups. But what of all the other security technology that has been deployed, acting as defense in depth, such as proxies, load balancers, network AV, IPS, anti-malware, WAFs, etc.? Well, one could argue that they are essential elements to a defense in depth model. The reality is they are there to plug the gaps in a model, which is predicated on the tenet that a network can be trusted. Clearly, that tenet is now defunct. The new model must be based on a new tenet, the exact opposite of the old, that the network can never be trusted. That is to say, we need to start with the principle of zero trust. Now let's elaborate on all of the fundamental tenets of the Zero Trust framework. This list is a short one. You might think it's a little too abstract, but I will expand on the detail in other presentations. For now, it'll do the job of providing clarity. So number 1, and top of the list, is the declaration that no network should ever be considered private. All networks must be considered hostile. You heard right. That includes all internal networks, core networks, server networks, data centers, private clouds, you name it. Any network behind a firewall, consider them all compromised. View all internal networks just like you would the internet in terms of trust, i.e. untrusted. Hence the definition zero trust. You should have zero trust in all of your networks. That is the starting point, the anchor to what comes next. So if the cloud HR service and the hybrid cloud mail service are always effectively sitting on the internet, how do we secure those services and associated data? That's where rule number 2 steps in. In simple terms, it says we never trust, so therefore we must always verify. That verification takes the form initially of validating the identity of the device, the user, the application. The second component of rule number 2 is authorize that user or app and that device and the requested network flow. Much of these stages we already do when protecting our systems and our data during internet-initiated connection requests, and we're pretty well versed in the practices and challenges of that. But the mindset change demanded now is to impose the same principles of defending inbound internet connections to all connections, regardless of their origin, be that private cloud, public cloud, core network, etc. All very well just espousing rule number 2 as a mandatory requirement. But authorizing any network connection is predicated on ascertaining an accurate level of trust. In practice, the whole zero trust system is founded on establishing the requisite level of trust. The establishment of trust in the real world is a non-binary calculation, calling upon a complex set of determinations. In fact, we're already pretty good at developing such trust policies. A direct comparison is with online banking. When the calculations needed to inject behavioral data in order to make a decision on whether we are allowing to commercially transact online, then similar decisions are needed to supplement the decision for allowing a connection. So on to rule number 3. As behaviour changes, trust levels must change, and this then impacts decisions on access, particularly for users, and perhaps less often, but no less important, for machine-to-machine communications. So accurate trust assessment is the goal, based on a complex set of determinations, some of which are dynamic. Policies must therefore be dynamic in nature. What you are granted access to today, from your corporate laptop sitting in your home office, may not be granted to you tomorrow. Same time, same place, same machine. Well, why not? Well, for example, you may have had a firm calendar entry to be on vacation abroad tomorrow, so your trust level was automatically lowered to reflect that. So these are the 3 rules. Number 1, all networks are hostile. Number 2, we must authenticate and authorize devices, apps and users, and network flows to compensate. And number 3, in order to do this, we must have dynamic policies reflecting real-world scenarios to obtain trust. If there is a number 4, we must all do this in real time. If this sounds like automation is going to play a pretty important part, you're absolutely right. Now let's look at those components which collectively form the new paradigm of the Zero Trust framework. Now this diagram may seem rather complex at first, but we're going to break it down in the next few slides. In this case, there happens to be a user with a device and a client application or service. But it is worth noting at the very start that the Zero Trust framework includes machine-to-machine comms, something that vendors of IDAM or CASB solutions conveniently ignore with their Zero Trust offerings. Understand that the user and the device can be geographically anywhere, inside the office, at a customer site, at home, Starbucks, etc. But geolocation is not irrelevant information. In fact, it is valuable to the decision-making process on whether to permit a connection request. But what is important to grasp from this diagram is the absence of any sort of private network. Instead, we have a data plane and a control plane, as represented by the different coloured clouds. Now, most of you listening are almost certainly going to be familiar with this concept, so I won't labour in the description. Suffice to say, the control plane is the decision-making system, which includes repositories for all the information sources that need to be queried. The control plane is almost certainly distributed across multiple systems, and it's worth pointing out that most companies will almost certainly have many of these discrete components necessary to establish this plane. The data plane is where the network connection takes place. It defines those systems, which includes, in this example, users, access devices, network components, application servers. This is also importantly where enforcement occurs to either permit or deny a connection request. Paradoxically, the decision-making process of a zero trust framework is entirely based on establishing the trustworthiness of that connection. To do this, when a user, their device and client app, which could just be a browser session, tries to connect in the zero trust secured system, the decision to allow that connection is dynamic. It establishes identity of the device, the user, and client app. It then has to make a decision on whether to authorize the flow based on the trustworthiness of all the combined user, device, app parameters, using data that it already knows or can ascertain at the time of the request. So components in the data plane, represented in this high-level diagram by an enforcement module, passes the authorization and network flow request to the control plane. Assuming it gets a good-to-go response, it will include policies that will secure and restrict the network flow end-to-end. These dynamic policies will include things like encryption and pinhole time-limited access control that ideally is fully monitored. We will now introduce the control and data plane components in a little more detail and elaborate on the process flows shown in the diagram so that you can gain an appreciation of how a zero trust framework fits together. Let's first delve into the two primary components, the enforcement module and the policy engine. Note that these two systems reside in their discrete planes. Having a policy engine in the data plane, or indeed on the same hardware platform or virtual system as the enforcement module, is a really poor design choice from a security perspective and should be avoided. The policy engine, residing in the control plane, must be highly secured, as indeed should all control plane elements. But why is that? Well, firstly, it is critical to providing access decisions. Outcomes are perhaps a yes, perhaps a no, perhaps a we need more assurances to elevate you to the requisite trust level. The policy engine is also fundamental in the formulation and distribution of dynamic policies, which it pushes out to the enforcement module once a yes decision has been reached against any single connection request. Policy elements are held in discrete repositories, as shown in the diagram, where they are loaded into the policy engine. Conceptually, we can identify two categories of policy. The first are broad infrastructure policy elements, which are used to filter out the noise, such as general inbound defense access control list entries that you might find on internet-facing firewalls. The second set are fine-grained policies. Such entries are likely to take into account the sensitivity of data, user, time of day, geolocation, device trust level, application trust level, etc. Of course, there has to be interaction between the control and data planes, and such communication must be kept limited and as secure as possible. In this case, we are talking requests from the enforcement module to the policy engine and responses back as detailed earlier. We will be delving into significantly more detail into the workings of these components in later presentations. For now, understand that these two components are key in assessing connection requests and invoking dynamic, ephemeral policies to control permitted traffic through to its destination. Now let's move on to the other two major components making up the control plane. We're now going to talk about trust engines and data stores. The trust engine is effectively a trusted advisor to the policy engine. it is used to conduct a risk analysis of a specific connection request and is used by the policy engine in making a final decision as to whether to permit. The trust engine needs to determine a numerical risk score for a connection request, and for that it needs information. So it leverages the information held in specific data stores. These also reside in the control plane and consist of distributed repositories such as user directories, device data such as CMDB, accounting logs which might describe details of the last attempt to the service from this user, and network data from flow logs. At this point, it is worth introducing the fundamental concept of variable trust. Most legacy identity and authorization mechanisms rely upon fixed trust conditions. For example, a client VPN solution trust model is usually along the lines of, if you authenticate against my domain, then you will be granted all the privileges associated with that account as if you were working from within the office building. That's pretty much a fixed or static trust model. Zero Trust moves us away from that model to one of applying a trust decision for every connection that user would like to make, and starting from precisely zero trust. That's why it needs to ingest a significant amount of information, much of which is dynamic in order to establish that trust. Information needed can include things like what service is the user requesting access to, data sensitivity, time of day, device type, device trust level. Other assertions might include establishing whether the device can support the requisite encryption profile requirements. All this information needs to be harnessed and condensed into a numerical risk score, which varies depending on real-time information. That is the essence of variable trust. But there is a lot more to it than that. Again, we're going to deep dive into these components and interactions between them in later presentations. Finally, let's just briefly sum. That just leaves me to say thank you for watching. You can find this presentation with complete speaker notes on ztsec.net, and the next instalment, part 2, will be combining user and device trust into something called the network agent.